Welcome to example number 6. We have a 15 centimeter long test tube of uniform bore that is lowered open end down into a freshwater lake. How far below the surface of the lake must the water level be down in the water so that only 1/3 of it is filled with water? We're assuming that the atmospheric pressure at the surface is 100 kilopascals. So let me draw a little diagram to kind of help you visualize this. We'll draw a picture of the test tube that is upside down in the water at the final position where it's 1/3 filled with water. So we're looking for this depth from the surface down here, and this is the air bubble here, and this is only, the water is only coming up 1/3 of the total height, so essentially 5 centimeters of the 15 centimeters. So what we'll first do is we want to know what is the relationship between pressure and volume. Because when the test tube's up here, at this position here, it's completely full of air. And so we have pressure at 1 is 100 kilopascals. And we'll call volume 1, I guess we'll just simply call it V. But then when you're down at this spot, the pressure is new. We don't know what that pressure is because it's down deep in the water. But we are told that the volume is now, well, it's 1/3 filled with water. So if we're considering the volume that's contained by the test tube, we'll be looking at really 2/3 of the original volume of the gas is now is the size. So it's been reduced to from V to just 2/3 of V. Now we'll have to make one important assumption. We will have to assume that the temperature is constant, and this is probably not true. As you go down deeper in the water, the temperature does indeed change, but in order to solve this problem, we'll have to assume the temperature is constant. So here's our methodology. We're going to try to find the new pressure down at this depth, and then once we know that pressure, we're going to use what we learned back in our fluids chapter to find the depth that it went down. So if we use the ideal gas law, PV equals nRT, and again PV equals nRT, we'll just rewrite it. We'll see some cancellations. So we'll assume that the number of moles is the same both beginning and the end because we haven't lost any gas, and the gas constant's the same, and we'll also assume the temperature is the same. So we really have a Boyle's law problem here. So since the temperature is constant, pressure 1 times volume 1 equals pressure 2 times volume 2. So pressure 1 is given as 100 kilopascals. Volume 1 is just V. Pressure 2 is what we're looking for when the volume has decreased to 2/3 of the original volume. The V's cancel out, and because pressure is inversely proportional to volume, we get pressure 2 is now 3/2 of the original pressure of 100 kilopascals. So that really means that pressure 2 is 150 kilopascals, or if you want that in pascals, that's 150,000 pascals. And now what we'll use is go back to our static fluids. We'll assume the fluid's not moving in here, and we know that the pressure varies with the depth within the fluid. So we're going to call this outside pressure P0. We'll just simply call it P1. So we're going to be using the formula P equals the external pressure plus the extra pressure due to the weight of the water, which is that hydrostatic pressure rho GH. So the pressure down at this depth is really pressure 2. The pressure at the top we've been calling pressure 1. And then we have rho GH. Well, we are in fresh water. I think that's written right here. Yeah, the fresh water. So the density of water, hopefully you recall, is 1,000 kilograms per meter cubed. So let's go ahead and substitute that in here. We have pressure 2, which is 150,000 pascals. Pressure 1 is 100,000 pascals. And then that's added to 1,000 kilograms per meter cubed times g, which is 9.8 meters per second squared, times h, and we're solving for h, which will be 50,000 pascals divided by 1,000 kilograms per meter cubed times 9.8 meters per second squared. And this gives you a depth of 5.1 meters. So if you were to take a test tube into the water and bring it down 5.1 meters down to that depth, then the air bubble will occupy 2/3 of the original space it was initially. And that's it for this example.